So I'd like to start by thanking Evdokia and Ranit for their flexibility in allowing us to move the Friday afternoon schedule into Wednesday morning. As a consequence of that, the start of the afternoon session will be pushed back, so Richard Murray's first talk will begin at 2 p.m. Evdokia is a key organizer of this program, and in particular is managing the last workshop in the program, which I assume is in good shape because I haven't heard anything to the contrary. And her talk today will be on algorithms, game theory, and risk-averse decision making.
Thank you, Dick. Just testing, is this microphone level okay? So this is meant, the title was meant to read a very brief introduction to algorithms, game theory, and risk-averse decision making, but as it is, it's quite long already. In the past 5 years, I've made a deliberate effort to connect to colleagues and researchers from applied disciplines outside of theoretical computer science, which is where I come from. In search for interesting algorithmic questions, and so I would typically start the conversation with, tell me what are interesting or important algorithmic questions in your field, and I would get an answer such as, well, find me an algorithm, design an algorithm to find the next supernova, or design an algorithm to balance the grid, or design an algorithm to incorporate solar and renewables into the grid so that the grid remains stable. And at this point, I would draw a blank, and I would think, well, I don't really understand what these problems are. I don't understand them in an algorithmic way, and I would just shy away and go back to my old and well-known algorithmic questions that I can make research progress on. Part of the goal of this program, to my understanding as a co-organizer and a long-term participant, is to help initiate or make further progress in this dialogue between theoreticians, in my case theoretical computer science, and our applied domains such as the natural sciences, energy, and transportation. And I realized that also from the past few lectures, that people outside of theoretical computer science don't really know what we do or what we know, what we're capable of doing. And to help facilitate that interaction, I would try to explain by giving a very brief flavor of sort of give an algorithmic tasting, such as wine tasting, in my mind of what algorithms, what interesting algorithms are. So since this is a workshop on real-time decision making, I want to start with a couple of examples that everyone can relate to. So this is a problem that I need to solve every day. When I was back at UT Austin, I needed to go to my office every day, and I would have to decide on what is my best route from home to the office. So on the left you see the real world map of part of Austin, and on the right is an abstract graph instantiation of this algorithmic problem. So that's, in algorithmic terms, this is called shortest paths. And everyone can relate to that. What is the shortest path from A to B? We have a very good understanding of that. That's an easy algorithmic problem. A related problem is one that UPS drivers have to solve when they need to deliver packages to multiple addresses. And again, a map on the left and an abstract graph representation on the right. If we are given distances between each pair of those addresses, what is the best sequence to visit the addresses so as to minimize the distance and the travel time, delivery time for the UPS driver? So that's another really interesting algorithmic problem, and it's a hard problem. So both of these, that's an instance of what's known as the traveling salesman problem. So both the shortest path problem and the traveling salesman problem are examples of graph algorithms problems. They are both really interesting. What's more interesting to me, what's intriguing is that one of them is easy, finding a path, which is a combinatorial object, a sequence of edges in a graph. And this other one, which is finding a tour, it's also a sequence of edges. It's also a different kind of combinatorial object, but somehow this second object is much harder to handle. So let me go back to very basic. So what is an algorithm? It's a step-by-step procedure to solve a problem. Many people outside of computer science think that computer scientists are programmers. And I want to clarify that theoretical computer scientists are a little bit different. So we are mathematicians. We think about what is the math behind the computer algorithm. And every computer program is the instantiation of some algorithm. And for us to be able to think productively about what an algorithm is, we need to be faced with a general but well-specified problem. So this was my challenge in my dialogue with colleagues outside the field. I wasn't able to get a well-specified problem in algorithmic terms. So here is the specification of the shortest path problem. I'm given a graph G with a set of vertices V and a set of edges E, a source node S and a destination node T, and edge costs. And this is the input. And I want to produce as an output a shortest ST path, namely a path with smallest total edge cost. So this to me is now a complete algorithm specification. And I want to emphasize again, the problem has a very clearly specified input and a well-specified output. And each such general problem has specific instances. For example, we see two different instances here. One is a portion of the map of Berkeley. The other one is a portion of the map of Austin with corresponding sources and destinations and different routes between them. So an algorithm has to be able to take every possible instance. So every possible map, every possible source and destination and edge costs, and produce an output, in this case a shortest path, with the desired properties. And one and the same problem may have many different algorithms for solving it that may be better, some for some instances and others for others. For example, Dijkstra, Bellman-Ford, Floyd-Warshall are all very famous shortest path algorithms. And more generally, we like to think about the world in abstract ways, ideally as abstract combinatorial objects. So you see here many examples of real-world situations and what the corresponding abstract objects are. So the example I gave, we had a network, transportation network, and the abstraction of that was a graph. And since graphs appear a lot in algorithms research, let me fully specify what we mean by a graph. So a directed graph, G, usually denoted as G, is a pair of two sets. The set V, which is a set of vertices, finite, and E, the set of edges, which is each edge is a pair of vertices. So a directed graph is one in which the edges have directions going from one vertex to the next. An undirected graph is the same thing, but the edges do not have directions. So we can, in the bottom graph, we can go from node 1 to node 2, and we can also go from node 2 to node 1. And the graph is the same thing as a network. We also use interchangeably nodes and vertices, and edges is the same thing as links, also the same thing as arcs. And so here is one abstraction of a transportation graph. That's a graph that gives rise to Brace paradox that I'll touch upon later. So we have 4 nodes, edges between them, and each edge has cost, which in this case denotes the travel time going from one node to the next. When I started trying to get into the energy domain, there I saw graphs that looked like that. And this led to a lot of confusion. So to a power systems person, probably this is the bread and butter, and this is a very simple electricity network. But to me, it isn't. So, they have these things that they call buses, and to me, a bus is a public transport vehicle. And it took me a while to figure out that a bus I can safely call a node in my language. And I still haven't quite figured out what a line is, whether it's an edge or a sequence of edges, but I have a semester here to figure that out. But to me, to be able to make some progress on any of those electricity networks, I need to see something like the graph on the left. So I really need to see nodes that look like circles or points, and edges that are just simple segments, lines that connect those nodes. And in this case, each edge has characteristics, resistances, line capacities, and so on that are specified as edge costs. So I believe that just this representation alone presents a big challenge for computer science theorists entering the energy domain. And hopefully we'll resolve this and many other challenges in the rest of this semester. So back to shortest paths, I want to talk a little bit more about the algorithm. First of all, what is interesting algorithmically? What is the algorithmic challenge? Even in a very simple graph like the one on the top, where you have n vertices and in a line, in a sequence, and each 2 consecutive vertices have 2 possible ways of getting from one to the next. If I were to find the shortest path from V1 to Vn, I could use a brute force approach. That's usually the first thing that we like to think of as algorithms, the most naive algorithm possible. So here the brute force approach would enumerate all possible paths, starting with the one that takes all the top links, then maybe one bottom and multiple top links, and so on. But this leads to having 2 to the n possible paths. And these are too many. So whenever you see a number that is 2 to the n, that is somewhat of a scary number to an algorithmist such as myself. So we don't like seeing numbers like that. To us, this would lead to a very inefficient algorithm. So we call this enumerating those paths would lead to an exponential running time. And why is this number so huge? Just to contrast, 10 to the power 67 is the number of atoms in our galaxy. So we want to stay away from numbers that, from running times that are exponential like that. Well, you might tell me there is something smarter that you can do for your graph on the top. We don't need to enumerate all these paths. It's sufficient to notice that going from V1 to V2, the bottom link is the faster one. Going from V2 to V3, the top link is the faster one, and so on, and chain this together. So that would lead to a much faster algorithm that only has an order of running time of n, the number of vertices. And indeed, this is the secret to why the shortest path problem is an easy one algorithmically. It's because it has this property called optimal substructure. It's the property that in the graph on the bottom, if we want to go from A to C and we find that the optimal route to do that is the red one, then when we just restrict going from A to B, the optimal still remains the red one. In other words, if we take an optimal solution and we take just a subset, a small part of this optimal solution, it would remain optimal for that corresponding smaller subproblem. And paths are not as straightforward as the graph on the top, because we might not be able to separate the graph cleanly into independent parts. So if we have a graph like that, we can't really do that. But still, Dijkstra's algorithm, for example, starts out by finding from the source what is the closest node to the source. So it finds that one, and then it finds the next closest node to the nodes we've already found, and so on. And this is why, very informally, we are able to solve shortest paths efficiently. So we are able to find them efficiently. So this is an example of a greedy algorithm. Other shortest path algorithms are examples of dynamic programming algorithms. And it's just a list of types of algorithmic techniques that we teach in undergraduate algorithms courses: divide and conquer, linear programming, and so on. And just to highlight again, when we don't know what to do, we usually resort to brute force or exhaustive search. And let me specify a little further. Algorithm running times are really important to us. So we are always after efficient algorithms or fast algorithms. But what do we mean by efficient? So there was a lot of thinking that went into that. I imagine it happened way before my time. Ideally, we want a definition of algorithm efficiency that's platform independent, instance independent, and of predictive value. If we have increasing instances, how much does the algorithm slow down? And so this is the definition that was arrived upon a few decades ago, that an algorithm is efficient if it has polynomial running time. So what's a polynomial? It's a mathematical expression like the one right below. So this is a polynomial in one variable n. It's basically some number times n to the power k plus another number times n to the power k minus 1, and so on. That's a polynomial of degree k, where k is some constant. We usually care about asymptotic running times, meaning as n grows very large, those second-order terms will become dwarfed by the highest one. And so we typically represent the running time by the highest order term. We say that our algorithm is order n to the k, where k is a constant. So when we talk about polynomial running times, it's simply order n to the power k for some number k. And so one example of a polynomial running time is n to the 100, even though to you that may seem like a really bad running time, and it probably is for big N. On the other hand, an expression like the blue one, n to the power 1 plus 0.2 log n, is not a polynomial. This is bigger than polynomial. So this would be considered an inefficient algorithm. And for not to begin, this is probably much better than n to the 100. So there is some debate between what efficient algorithms mean in theory and what they mean in practice. There is not always a one-to-one match. As another well-known example, the simplex algorithm, which is the most used algorithm for linear programming, has exponential worst-case running time, while we do have an efficient algorithm that runs in polynomial time for linear programming, but it's not considered a practical one. So there are some disparities between theory and practice here, but generally polynomial has stood the test of time and has turned out to have a good indication. And one advantage to it is also that the definition is easily negatable, meaning I can tell you what's inefficient as well, something that runs that takes longer than polynomial time. And so that brings me to our most famous problem, P versus NP. P is the class of problems that can be solved in polynomial time. In other words, we can give efficient algorithms for them. NP, contrary to a popular belief that it means non-polynomial, it stands for non-deterministic polynomial. And it stands for the class of problems for which we can verify that a given solution is correct in polynomial time. And specifically, P is a subset of P. And here I want to insert many thanks to the help of my PhD student Ali, who is here in the audience and here at Simons this semester, for the many beautiful pictures that you see on these slides. So this picture is due to him. Is one example of a polynomial time solvable problem. We have Rubik's Cube. Ordering an n by n by n Rubik's Cube admits an efficient algorithm. Sudoku, on the other hand, is not known to admit an efficient algorithm. However, if you give me an answer to Sudoku, I can quickly check. I can add up the numbers and verify that your solution is correct. So Sudoku is an example of a problem in NP. And there are many other problems beyond NP. For example, chess. If you tell me what is my next optimal move, I cannot verify that in polynomial time. But in any case, a lot of our tools are for problems in P and NP. And a lot of the problems in the real world fall in this category, so that's what I'll focus on, problems within P and NP. So let me clarify further this difference between what it means to solve a problem and what it means to verify a candidate solution in polynomial time. So, for example, back to shortest paths, is there a path in graph G from a given source node to a given destination node with at most k edges? For example, down on the bottom, I may ask you, is there a path with at most 5 edges? And you may take some time to look at this graph and try to solve it. Well, again, that's a shortest path, so that's an easy problem algorithmically. And verifying a solution is even easier. If I give you a path, you can see that it indeed has 5 edges, so the answer is yes. So I can verify the solution much easier than I can find it and I can solve for it. Back to the traveling salesman and a related problem, Hamiltonian cycle. So Hamiltonian cycle in an undirected graph is a cycle that visits every vertex exactly once. And for solving a problem, here is a problem, is there a Hamiltonian cycle in a given graph G? And so you see the graph on the left gives you one in which there is such a cycle, and the one on the right, there isn't such a cycle. So this is a hard problem. If you give me a graph, it will be hard for me to come up with a cycle or just answer whether there is a cycle or there isn't. But once you give me a cycle, I can easily verify that such a cycle indeed exists. And currently, even though verifying a given solution, that the given solution is correct, seems like a much easier problem than solving the problem in the first place, no one has been able to prove that it is easier. And so this is informally our biggest open question, whether P is equal to NP. So is the class of polynomially solvable problems the same as the class of those problems for which we can verify a given solution in polynomial time or not? And given that we don't know the status, we go on to further categorize problems in NP, such as the NP-complete problems. So NP-complete problems are informally the hardest problems in NP. They have a property that if any NP-complete problem can be solved in polynomial time, then all of them can be solved in polynomial time. So if someone tries to prove that P is equal to NP, all you need to do is find one NP-complete problem that you really like and you find that you're able to think about and come up with a clever, efficient algorithm for it, and you will have resolved the biggest open problem in theoretical computer science. And a little further on NP-complete problems, so slightly more formally, a decision problem, one to which the answer is yes or no. Is NP-complete? If it is in NP, so we can verify a given solution is correct in polynomial time, and it is at least as hard as some known NP-complete problems. So we have a strict way of defining mathematically the notion of at least as hard, but that's as far as I'll go. And so to prove that the problem is NP-complete, we just have to find another known NP-complete problem, show that our problem is at least as hard. And every problem was shown to be NP-complete in the same way. except for the very first NP-complete problem, which was a real breakthrough. But it means that from any problem that we show is NP-complete, we can trace back a path down to that first one. And all of these steps were very precise algorithmic transformations. And this is why, if you find just a single NP-complete problem and give a polynomial time algorithm for it, you'll at once have solved all of the known NP-complete problems. And so when this is very deeply ingrained in us as theoretical computer scientists, when we see a new problem, a well-specified algorithmic problem, the first thing that we want to understand is whether this problem is in P, does it admit an efficient algorithm, or is it NP-complete or in some other complexity class. And there are many other complexity classes. I will just stick to P and NP-complete, but just so you see, this is a very small sample of the many complexity classes that exist. So you see P in red and NP in yellow. There is also randomized polynomial time, exponential space, and so on. And if you're more interested, I would invite you to Google Complexity Zoo. There is a web page on Wikipedia which details the many complexity classes and the relations to them. And so this is part of research on computational complexity, is to understand the relations between different complexity classes. So the P versus NP problem is not just an open problem in theoretical computer science. It's now been listed as one of the Millennium Prize problems by the Clay Mathematics Institute. So you see it appear down here. It's just a portion of the website, and there are 4 more problems down below P versus NP, but you see that appear as problem number 3. If you click on it, you will find more detail about the problem. So each of those 7 problems, known as Millennium Prize problems, will get a reward of $1 million if you come up with a solution for them. So it's now considered as a very fundamental and important problem in mathematics as well. But it's not just a problem of great theoretical interest, it's also of great practical importance, because if you prove that your problem is NP-complete, that means that you shouldn't waste time looking for an efficient algorithm, well, unless you're really passionate about it. Maybe you find one, in which case you will have revolutionized the area of theoretical computer science and mathematics. But typically, if you encounter an NP-complete problem, then again, we don't just stop there. We look for efficient approximations, heuristics, and so on. And what do I mean by efficient approximation? So an approximation algorithm is a polynomial time algorithm which doesn't give us the exact answer, but it maybe gives us a near optimal answer. And we like to understand how much near the optimal we are. And so formally, an alpha approximation algorithm for an optimization problem is one that runs in polynomial time, returns a correct solution, be it a tour or some other combinatorial object. And the cost of this solution is at most alpha times the cost of the optimum. So even though we don't know how to find the optimum, we can guarantee that we'll be that far from it. And as an example, back to the traveling salesman problem, which I mentioned at the beginning and which I said is hard. So it's a known NP-complete problem. That's the formal description of the problem. Again, you just need to find a tour of the cities or addresses for UPS delivery so as to minimize the distance, or in the decision version, so that your distance is at most some budget B to be traveled. So just to mention, this problem is in NP, because if you give me a tour, I can add up the distances and verify that they add up to no more than my desired budget, my total travel time. So if I'm given a version of this problem, metric TSP, has a set of cities and distances that satisfy a triangle inequality. That simply means that going from city A to city B will take you no longer than passing through city C on the way. One way to approximate this problem, since we don't know how to solve it exactly in polynomial time, is to find what's called a spanning tree. A spanning tree is just a set of edges that form a connected graph, and there is no loop, there is no cycle. So an example of a spanning tree is the set of edges that are in bold black on the figure. So we find the minimum spanning tree, one with total minimum edge cost, and then we just go around it twice. And that gives us a tour. That gives us a little more than a tour, because we then end up visiting some cities more than once. And to prevent from doing that, we just, once we get to a city for a second time, we just skip that city and move on to the next one. So we eliminate those repetitions, and we end up with a tour. And this tour turns out to be a two-approximation algorithm for the traveling salesman problem. Because any tour would cost more than a minimum spanning tree, and paying twice the cost of minimum spanning trees would guarantee us to be no more than twice the cost of the optimal tour. If you missed the last part, don't worry about it. What I wanted to illustrate mainly is what we mean by approximation algorithms. And to give you just a brief example of a cute approximation algorithm that is fairly easy for a really important problem, the traveling salesman problem. So I started out with shortest paths, and the shortest paths is my running example for the entire presentation. And I said that shortest paths are easy. However, they're only easy if you abstract away the realistic challenges that maybe your optimal route doesn't just depend on where you go, but also on where everybody else goes. And so this means that in addition to thinking about how to compute shortest paths algorithmically, we need to also worry about strategic considerations. How would other people affect the outcome that we see, the length of our shortest path? And so this brings us to, again, a really brief tasting of game theory. So game theory, unlike what many people think that they link them to video games, they have not much to do with video games, but it's a mathematical field which studies the strategic interaction of people. And one way to think of games is as thought experiments, which help us learn how to predict rational behavior in situations of conflict. And this is what I mean by those three highlighted colored phrases. By situation of conflict, I mean that everybody's actions affect all the others. Rational behavior means that I, as a participant in the game, simply care to optimize my own benefit. So games, rational behavior doesn't capture altruism, envy, and other such human behaviors. And by predict, I want to know what is the outcome of a game. So when people interact in a certain way, what will happen at the end? And those predictions are called solution concepts, and the most famous such solution concept is the Nash equilibrium. There are many others. And so back to shortest paths, now that additionally capture this strategic interaction through congestion. So the reason we have to worry about others, what paths others will select, is this phenomenon of congestion, which basically means that the roads are shared resources, and the more people use a given road or a given edge in a network, the travel time tends to increase. And this congestion phenomenon has unfortunately led to a lot of waste of time and fuel captured by congestion costs that were measured to be $116 billion in 2014. So this is why transportation is such a prominent area, I think, in this program, and it's labeled one of the areas of national priority to improve. So game theory provides us a way to understand congestion and hopefully at the end give us some insight on how we can alleviate congestion. That's why we study them. And I'll illustrate, I won't give an overview of game theory as a whole, but I will focus on congestion games. So through an example to start with, suppose that we have 100 drivers that want to go from town A to town B. And I have captured this congestion phenomenon, the fact that travel time increases if more people use a given link, by having this variable x appear as in the travel time on some of the edges. So x here stands for the number of drivers that go on this particular link. And so if I have all 100 drivers go on the first link on the top, that means that this link will take 1 hour to traverse. Whereas if 50 drivers go on the top link, then everyone will experience a delay of half an hour. So again, this is just an abstraction. So 2 links have this congestion effect, and the other 2 take always 1 hour. They don't suffer from this congestion phenomenon. And the question is, what would be the resulting traffic pattern in this situation? And probably everyone can spot quickly that those 100 drivers would split 50-50. So 50 drivers will go on the top and 50 drivers will go on the bottom. And this will be an equilibrium situation because in this way everyone travels 1.5 hours. There is no incentive for anyone to switch to the other route because it takes the same amount of time. In contrast, any unbalanced traffic pattern, if I had 40-60, 45-60, and so on, one of the routes would take shorter than the other, and then people would have incentive to switch. So that would not be an equilibrium situation. Well, notice that in this traffic pattern, the 2 bolded links would take half an hour each. And suppose now that you have a benevolent mayor who wants to improve efficiency in the transportation network, so they decided to connect those 2 faster segments to make it faster for everyone to reach from town A to town B. So they build a superhighway that takes 0 hours, connecting those 2 vertical links. And all of a sudden now, this superhighway becomes beneficial for everyone to use, so everyone switches to use the zigzag route indicated in light blue. And indeed, this will be the resulting traffic pattern. But under this traffic pattern, when all 100 drivers take the first top link, this top link now would take 1 hour to traverse, and same with the last bottom link. And so the total delay that everyone experiences now is 2 hours. So instead of improving the situation for everyone, the situation became worse. That's called Brace paradox, the phenomenon that adding a link in a network may sometimes deteriorate total travel time. So what happened here is that, let me first actually verify for you that this will be the resulting traffic pattern. Does anyone have a question on that? So it's an easy exercise to check. Why wouldn't we have anyone go just on the top or on the bottom route as before? Well, they would compare their zigzag route with the alternative, and on the non-overlapping parts, they would compare x over 100 and 1 hour. X over 100 with 100 drivers is always less than or equal to 1 hour. So switching to the top or the bottom won't give them any benefit. So everyone will stick to this zigzag route. This is the equilibrium situation. Well, of course, they could do as before and have the 50-50 split, but that's not an equilibrium anymore. But it is what's called a socially optimal traffic pattern, the one that minimizes total travel time. And the fact that equilibria may be inefficient, and here inefficient means something very different from inefficient algorithms. So inefficiency of equilibria means how far are you from a socially optimal situation, one that maximizes everyone's total benefit. So that's an example how equilibria can be inefficient. So that's another challenge beyond the computational one, the algorithms. Well, here you see that the equilibria is basically 33% more costly than the socially optimal traffic pattern, where everyone splits half and half. And this was quantified as price of anarchy, so that's a measure of how inefficient equilibria are, how far they are from this socially optimal situation, formally defined as the performance of the system in the worst Nash equilibrium over the optimal performance, the one that would arise if a central planner directed where everyone should go so as to minimize total travel time. And just to revisit again, so I'll give definitions through pictures. I had previously more mathematical definitions, and my students who listened to my practice talk said, no, remove all the math. Wardrop is the one who studied this model of congestion games, and he came up with two principles. The first one was that travel times on used routes should be all equal and no greater than travel times on unused routes. And this is essentially the definition of Wardrop equilibrium. So he didn't call it so, but it acquired his name. It's equivalent to Nash equilibrium. Nash was working on his equilibrium concept in parallel, so those were around the same time. It's also called user equilibrium. And so again, Wardrop equilibrium is a traffic pattern where everyone travels along shortest paths. So again, an example of equilibrium here is where everyone takes this zigzag route. And as we said, this would not be the socially optimal traffic pattern, so that was Wardrop's second principle, that the average or total journey time should be minimum. Well, this is a desired traffic pattern, but not one that users would arrive on their own to, and it's known as the social optimum. So again, that's a traffic pattern that minimizes everyone's total travel time. And the social optimum in this picture is the one with the superhighway included, is the one where everyone splits 50-50 and ends up traveling 1.5 hours on average each. And something that came out of this framework, very elegant mathematical derivation, was that social optimum could actually be seen as having a similar definition to an equilibrium. So rather than saying the social optimum is the one that minimizes total travel time, you could say, oh, actually social optimum is a traffic pattern under which modified travel times on used routes are the shortest, where the modification is the addition of something to the travel times. This addition could be interpreted as tolls. So if we were to add those tolls in green to the two fast links from before, if we added 1/2 to each, you can verify that this now is an equilibrium in this network, whereas it wasn't before. And this allows for an interesting mechanism design interpretation that if we add tolls to the network, appropriate tolls, we can drive people of free will to reach on their own the socially optimal traffic pattern. And that's indeed the goal of mechanism design. So mechanism design is a sister field of game theory. You can think of it as the inverse of game theory. It's the study of how to design the rules of the game so as to guide people to an outcome that you want them to reach, such as the socially optimal traffic pattern here. And again, just as a reminder, I mentioned that before, but price of anarchy was a way, a measure to quantify how far equilibrium can be from the social optimum. It measures the degradation of system performance due to, you can call it free will or selfish behavior, whichever is your favorite expression. Selfish behavior caught on as an expression in algorithmic game theory. It was measured, it can be shown with a very simple and elegant proof to be 4/3, not only in the example we saw here, but in general graphs, so long as the delay, the travel time as a function of the number of drivers on the link is linear. And you can derive also expressions for other types of delay functions. So just a few takeaway points on congestion games. So I started out with my running example of shortest paths. So I said shortest path is an easy algorithmic problem, but it becomes more challenging when you think of multiple users in a network, all sharing the same resources, the same roads. Here, fortunately, congestion games are one example where both the equilibrium and the social optimum exist and can be computed efficiently via convex programs. In general game theory, this is one big challenge. So in a game theory model, the first thing you want to establish is whether an equilibrium exists, and if so, can you compute it in algorithmic game theory. So here we can compute them, and the good news is that not only can we compute them, but we can arrive at a social optimum if we introduce this additional modified travel times, which we can interpret as tolls or some other mechanisms. And again, price of anarchy is a quantification of the inefficiency of equilibrium, and it can help guide us whether an intervention in a system is necessary by way of mechanism design so as to guide people to a more optimal outcome. So another one complication of shortest path is when you have multiple people, when you have strategic behavior. Another complication is when you have uncertain travel times. So we are slowly starting to add more practical considerations to the problems. So if we have uncertainty, here is a toy example. What would be the shortest path here? Well, shortest path is not well defined, first of all. So let's say we are going to the airport, and we can either take BART that, let's say, doesn't run into any congestion issues and always takes 40 minutes, or we can take a cab, which again, to simplify, will take half an hour or 60 minutes with probability half and half. So which route would you prefer? I haven't specified the problem fully. So if I were, in addition, to tell you that for your flight you have to be at the airport by 10:30 a.m., now that might give a little more insight. Or if you leave before 9:50, if you give yourself more than 40 minutes for your trip, then the BART option seems like the sure thing, the better option, because you get there 100% on time. However, if you forgot your passport or other document, ran home, and now all of a sudden it's 9:52, the BART option will get you late for sure. And so now your only chance of getting to the airport on time is the route by cab, even though it gives you only 50% of being there on time. And so the notion of optimality here differs. So shortest paths are not well defined under uncertainty. You have to come up with some kind of objective function. And here our objective is to arrive to the airport on time or minimize our probability of being late. And this is a result of risk aversion. So when we encounter risk, oftentimes we are risk averse. And this would bring me to what we mean by risk, how we define risk. But just again, to conclude this example, risk critically affects how we define what an optimal route means. And sometimes, being risk averse, we may be forced into choosing a risk-loving situation. The route by taxi has both higher mean and higher variance. And so we may be forced into a gamble because this is the only option that gives us some positive probability of arriving on time. And so that's why I talk about risk. Risk can critically affect our design of algorithms, our analysis of game theory models and mechanism design. So a little bit more on, so what is risk? So everyone informally understands risk. But mathematically, there is no one agreed upon definition of risk. So it depends on the application, it depends on the situation. And here I'll just mention very briefly different approaches of quantifying risk from different fields, economics, finance, and modern risk theory. So in economics, risk is captured or measured through expected utility theory. So the idea that you can express preferences over random variables or lotteries by mapping each one to a single number through what's known as a utility function. That's a very old concept that predates expected utility theory. Bernoulli in 1738 already had suggested that. And such a utility, though, exists if you assume given axioms. I won't go into the definitions of those axioms. And it turns out that those axioms fail in reality. So expected utility theory doesn't necessarily capture how people actually behave, though it's a useful prescriptive theory. So where it fails is people are given this experiment. So in the first situation, a group of people were asked to choose between a lottery that gives them $55,000, think of that as your annual salary, with probability 33%, or $48,000 with probability 66%, and 0 with a small 1% probability. So either choose that or choose $48,000 for sure. So which one would you choose? Maybe we can do a poll of hands in this room. Who would go for option 1? Oh, there's a lot of risk-loving people here. Maybe your income is a lot higher than these numbers. But who would go for option 2? So in the experiment that was performed, here I saw roughly equal show of heads, but in the experiment that was performed, most people tended to choose the sure thing, the $48,000. And when that same group of people was asked to choose between a modified problem in the second situation here, so either get $55,000 with probability 33%, 0 otherwise, or $48,000 with probability 34%, 0 otherwise. Most people who had previously chosen the sure thing, the $48,000, now chose the $55,000. To them, a 1% difference in the winnings didn't make much difference, and $55,000 looked much better. Well, this is a contradiction with expected utility theory, because if you try to map that mathematically to a utility function to be able to derive the resulting preferences, you'll arrive at a contradiction that no such utility function exists. And that's a contradiction with this independence axiom. In any case, so these are well-known criticisms of expected utility theory, but it's still a good prescriptive theory that is one way of capturing and defining risk aversion or risk-loving behavior. So for example, convex utility functions are used to represent risk-loving preferences, and concave utility functions are used to represent risk-averse preferences. In finance, a different approach was taken independently. So Markowitz, who was the first one to quantify risk of a portfolio, identified risk with the variance of a portfolio, and postulated that if you want to minimize risk, you should minimize the variance of your portfolio subject to some threshold that you want to achieve on your return. So in shortest paths, our running example, that would mean some examples under this framework would be minimize the mean plus standard deviation of travel time. So that could be one definition of a risk-averse shortest path. Another one could be minimize the variance such that the mean is at most a given threshold, or minimize how much time you allocate for your trip such that the probability that you exceed that is no more than, let's say, 5%. So this is the well-known value at risk criterion that's used widely by financial institutions. And there are multiple others that fall under this framework, but basically they're all involve some combination of mean and variance. And some of the criticisms of this theory is that it may lead to non-monotonic paradoxical preferences, For example, if you have two paths to choose between, one always takes 1 hour, the other one takes always 1 hour or 50 minutes. The second one is strictly better. However, the second one is penalized by this objective function at the top because it has a positive standard deviation. So it will end up having a bigger risk according to that definition. Also non-convexity, which some people link to risk diversification. And so as a result of those criticisms, a modern risk theory was developed axiomatically where researchers stated what are desired axioms for risk aversion. And not to go through them, but just one example of this is the conditional value at risk. So I mentioned the value at risk being how much time do you budget for your trip so that the probability of being late is at most 5%. Well, here in the conditional value at risk, we don't just care to minimize that threshold. Probability we are late is at most 5%, but how much late we are beyond the threshold matters. And so we want to minimize the expectation of lateness, the expectation of that probability tail. And just one remark that when a random variable is normally distributed, this conditional value at risk, which is now one key such called coherent risk measure satisfying those axioms, is actually equal to the mean standard deviation objective. So back to algorithms. So what definitions of risk should we use for our algorithmic formulations? Well, it depends on the situation. And we really can't use all of them at once. They all would require different algorithmic approaches because they have different mathematical properties. But pretty much all of them lead to a new challenge with shortest paths. For example, I mentioned that that's an easy algorithmic problem because of optimal substructure. The fact that if the optimal route from A to C is the red one, the optimal route from A to B is still the red one. So this no longer holds if you, for example, want to arrive to the airport on time, or if you want to minimize the mean plus standard deviation of your path. So if you want to minimize the mean plus standard deviation of your path, if you are just going from node A to node B, you can add up the numbers and see that from A to B, the better option is the blue link. It has a total 7.9 versus 8. And if you do the calculations going from A to C, the better path would be the red one. So we now see that a portion of an optimal solution is no longer optimal for the smaller problem, and we cannot use dynamic programming and basically the approaches that allow for efficient algorithms. And the challenge here is really that we are going from originally a linear objective function for shortest paths to now a non-linear, in this case it's even non-convex objective under this mean standard deviation risk objective. So what could we do just to give a little glimpse? In this case, it's a very different algorithm, and the key insights are three. One is to map your whole problem onto the mean variance plane. That means I'll represent all my feasible paths as red dots on this diagram. So each red dot corresponds to a path with x coordinate equal to its mean travel time and y coordinate equal to its variance. And then observing also the visualization of the objective function through those parabolas that you see. Higher objective function value, higher mean standard deviation corresponds to a higher parabola. And so the best path is the red point that lies on the lowest possible parabola, the one that touches over there. And so how do we find that path? Well, we can't really find it. We don't know how to find it efficiently. That's an open theoretical problem, but we can enumerate all the candidates, all the paths with mean variance pairs sort of on the lower left, and pick the best one of them. And this leads to an algorithm that has running time n to the log n, and if you remember definition of efficiency, that's not polynomial, that's higher than polynomial, so that's not considered an efficient algorithm. It's also likely not NP complete because that's less than exponential time. So it's still an open problem that's intriguing to me personally, whether this problem is in P or not. In any case, there are ways around this inefficient worst-case running time by approximation, so we can approximate this arbitrarily well and find a path that's arbitrarily close to the optimal path. And we can do so for not just shortest path, but for various combinatorial problems and several related risk-averse objectives. And here I want to mention that even though I'm talking about risk, the main challenge is that we transfer the uncertainty and risk into a nonlinear objective. So many problems that are traditional in algorithms are linear, and with risk they become nonlinear, non-convex, and that's just an example of a problem that we arrived upon that I find really interesting in the power grid. It's basically finding a spanning tree with a nonlinear objective. I'm not going to explain it, so these problems are really interesting algorithmically. What about game theory? How does this change the congestion game model that I told you? Previously I said that equilibrium is at most 4/3 higher cost than the social optimum, so at most you end up traveling 33% more in total travel time. Well, if you add uncertainty now when you consider different risk-averse objectives captured by those different list of models there, Wald, Savage, and so on. So these are different risk-averse objectives. The price of Anarchy would be very different. So the takeaway from this slide is that you may end up having very different numbers for the prediction of your system performance, from a small constant to unbounded. And so the takeaway from this slide is that risk very much affects the predictions of system performance. So we need to be very careful how we model risk and incorporate it. And further, how we analyze things with risk may become more challenging. Here we were interested in understanding how much risk alone contributes to the degradation of system performance, to increase travel time of commuters, than selfish behavior alone. And so we thought of comparing a risk-averse equilibrium, one in which users select minimum risk paths, versus a risk-neutral equilibrium, one in which users just minimize their expected travel time. And we want to see how much longer in total those risk-averse users travel. And so they end up traveling more by this factor over here in the highlighted yellow box. So to me that was interesting algorithmically because the answer depended on the network topology. So this eta is something that depends on the network topology. 1 for series parallel graphs, 2 for the Braze graph, and up to number of nodes over 2 for general graphs. R is the level of risk aversion of people, and K over there is how much bigger the variance is compared to the mean. Let me mention just one slide on mechanism design, how risk changes things there. So yesterday we heard a fascinating experiment that Balaji did with the outcome that people tend to respond much better to lotteries. So we heard the example, for those of you who didn't hear, in recycling, for example, if you get 5 cents to return a bottle versus if you are promised to get $100 with a small probability, people will end up recycling more if they are given this lottery. So this captures the fact that for small amounts of money, people tend to be risk-loving, so they respond better to lotteries. Well, it turns out this is really not well understood in theoretical mechanism design. So what are the optimal lotteries? Should I offer you $100 with a small probability? Should I offer you a basket of options, 100 with a certain, 50 with another, and so on? That's not well understood. So we are currently studying that with my postdoc, Manolis Punturakis, who is a fellow here at the program, and he is extremely well knowledgeable both on this, and he's worked on mechanism design with risk-averse agents, so I encourage you to talk to him more for more details. But let me conclude. So I attempted to give a taste of the types of tools we have in theoretical computer science and what we find intellectually stimulating. And my hope from this program is that we have a dialogue with researchers outside theoretical computer science, be it other theoreticians or experts from our domains, natural sciences, energy transportation, where I hope for a win-win situation. But that situation is not easy. So we, theoretical computer scientists, want to somehow abstract clean formulations from the more practical problems. And I think in turn we have a lot to offer. We have a lot of tools and a way of thinking that would provide insight into hopefully solving some of the more practical problems. I won't mention open questions. There are many, but I'll leave for this semester-long program to ask the questions. So thanks very much.
Thank you very much. Questions?
There's a question. Yeah.
Yes.
Mainly a comment just regarding real-time systems. Most of the definition of efficiency of algorithms are from the 70s and 80s. And today, for example, the input is not of size n, just an infinite stream, especially in real-time decision-making. And when we work with drone or EEG signal for the brain, n squared and 2 to the n, it's the same thing. It's totally impractical. We need actually linear time or near linear, or as Ronit will talk in the next presentation, we actually usually off and it's much too much. We need sublinear time. And another thing is that we have now clouds. So communication issues and parameters are also now very important, not just running time. And mainly last thing, I think the most important thing is development time these days, more even than running time sometimes.
Sorry, which time?
So there is the running time. If it's very slow, say 10 times what you want, just buy 10 computers on the cloud and it's 10 times faster. But the development time, finding 10 students instead of 1 is sometimes much harder than finding 10 computers instead of 1. So the time to implement the algorithm, so you have n log n algorithm, which is trivial, a few lines, and of n algorithm with 10 pages that will take years to implement, and then the constants will kill you. So that's on the bad side. On the positive side, the big data and real time really now support the O notation, because once people say that, you know, if you write in C compared to Python, the constants are very important and the O notation kills it. But when you handle big data, n is really, really very large and infinite, so the O notation makes sense, and you don't care too much about the constants. And again, if it's too slow, the constant, just buy a constant number of computers on the cloud, and you can kill this constant, but you cannot kill the O factor. So there are good things in the classic definition, but some not so updated notations. That's all my only comment. Thank you.
Thank you for the comment. I think that is an excellent way of starting a dialogue, and a great preview to the next talk.
Yeah.
Yes.
Yeah, I think the themes you've raised will be discussed throughout the whole program. They're very important.
I can see.
Yeah. Other questions?
I find Braze's paradox a beautiful idea and intriguing and engrossing, but when you begin to try to apply it to actual transportation networks, you have to confront the fact that we don't actually have roads that have zero travel time, or roads that have no sensitivity to congestion. And I have tried in various ways to find a way of, an intermediate way between the abstraction and the messiness of actual highways. And I've had interesting results, but nothing that's provable or even readily expressible in some closed form. But obviously, if this is to be of practical use, you have to find some way to map from the real world to those abstractions. Can you offer us any guidance on how to make progress in that direction?
Well, let me repeat the question. So the comment that Braze paradox that I showed is a nice, cute mathematical model, yet how does it map in practice? While I will not tell you, I will not want to attempt to tell you right now how to go from this theory to practice, I'll defer to some of my transportation colleagues who have a lot of insight. But I will say that Bayes paradox does arise in practice. With just a curious anecdote, I read, I think, in the New York Times, how at some point Broadway, a portion of Broadway was closed in Manhattan, and everyone feared that this would lead to tremendous congestion, and then once it was closed down, traffic flow improved. So
the New York Times account of that is the only extant publication on that observation. And there was absolutely no before and after documentation. There were no counts of actual travel times or anything. It was an offhand observation by a traffic engineer.
quite possibly, yeah.
Actually, there was a paper written in 2009 that said that this kind of phenomena was observed in London
Yes.
and in some other cities as well. It's a 2009 paper. And
Yes, and it's also lacking in verification.
Okay. I didn't know that.
Good.
Just to add to that point, in the context of Bayes paradox, not in the context of transportation, but in the context of power grid, there has been numerous such incidences in the context of when people are trying to expand the power grid, for example, to accommodate more renewables in West Texas or coastal California, with the good intention of strengthening the arbitrary power transmission line, may lead to a unintended consequence of reduced network capacity. And there are many such examples. I'll be happy to show you offline.
Yes.
Over there.
So I didn't fully understand that you seem to be stating a theorem, I think, that you could take any transportation network and add constant tolls on various links to ensure that the equilibrium is the social optimum. Is that correct?
That's correct. I didn't put forward a precise mathematical statement. But that's correct.
Okay, let's take our break and resume at 11 o'clock for Ronit's talk. Thank you again.